Welcome again to Beyond the Clouds Edge to Edge Transformation. And transformation takes a lot of people from various walks of life. We need the industry, we need the government, we need the academia. All of us have to come together so that we can make this transformation possible. It's a joy for me to talk to Dr. Subhasish Mitra of Stanford. He has been one of those people who crosses over from the academics into other walks of life as well. Subhashish, how did you become the Subhashish that we all know today?
Shankar, thank you very much for inviting me to join this wonderful video cast. I grew up in India. I studied engineering over there. I came to the US for grad school and I got my PhD in the US. I was at Intel for very few years, close to 4 years. I joined Stanford as a faculty, so it's very simple.
Subhashish, you're being very modest. I also started my career at Intel in the chip industry. So you worked in the industry and decided to go back into the academia. What propelled you to do that?
When I was finishing my PhD, my advisor was a very famous professor. I applied for faculty positions at some major places in the US. I was fortunate that I had multiple offers. I was almost ready to be a professor. My thesis advisor told me that he felt that every engineering professor should spend some time in industry doing real stuff. He told me about his life story, and he actually did that sort of thing. He suggested that maybe I should go to Intel. I was shocked that he would suggest something like that. I went and told the universities that were making me offer that I'm considering that. And so the universities said, well, why don't you take a leave of absence, be at a company for 2 years, come back to us. I went and told my thesis advisor about that. He said that was a terrible idea. If you were at a company and you were on a leave of absence, nobody would take you seriously because you would always be an outsider. If I really wanted to be in a company, I should be 300% in that company. My friends were kind of shocked. And they were telling me that, are you crazy? Nobody gets these kinds of academic job offers. What happens if you do not get such offers in the future and if you want to be a professor? So I went back to my advisor and also one of my dissertation readers. He looked at my CV. Given the number of publications you have, you can survive in industry around 4 years without publishing anything. If you want to go back to academia, you do it within 4 years. That's how I went to Intel.
I've known Professor McCluskey for a long time, and Quinn McCluskey algorithm formed the basis of digital electronics for most of us, the Carnot maps and all that.
He was the father of computer engineering.
That explains why a lot of your research is very pragmatic. Can you tell us a little bit about the research work you've done and how it has found its way to applications in the industry?
I'll start from what I did at Intel. You will see that what I was doing at Stanford before Intel, how that becomes very relevant. When I joined Intel, this was early 2000s, there was actually a very famous chart by the CTO of Intel, Pat Gelsinger, who is now the CEO of Intel. The chart was about Moore's law. The manufacturing cost per transistor was going down per generation. That was what would be called Moore's law. But the testing cost per transistor was roughly constant over generations. Gelsinger actually published a paper which was based on a keynote that he gave at ITC, the International Test Conference. It showed that roughly around 2015, the test cost would exceed the manufacturing cost per transistor. And since the test cost per transistor was flat, that would be the end of Moore's law. He called it a frightening future for the industry for obvious reasons. When I joined Intel, they showed me that chart. They were asking me what could I do to address the question. And the question was essentially about the manufacturing test time and the manufacturing test data volume. And test time and test data volume are again intricately related in the way the industry does things. There had been work from IBM and other places on what is called built-in self-test. For some fundamental reasons, those techniques were not very applicable. And since you come from a design and testing background, you probably will appreciate this. How do you test something? You send in a whole bunch of bits. You observe a whole bunch of bits that's coming out of your chip, and you have to say whether this chip is working or not by looking at the response and comparing it with some golden response. The typical ways of doing testing is what is called scan, design for testability. Essentially what happens is as the chips get bigger and bigger, the amount of time that it would take to send in those ones and zeros into the chip and looking at the ones and zeros that are coming out of the chip, that just goes up drastically. So that increases the amount of data that you have, and that increases the amount of time. You have to cut down the amount of data that you are sending. Many people call it test compression. You have to also cut down the amount of data that you are observing. Generally, we are talking about digital systems, so the real chip actually produces ones and zeros. If all your responses that you predicted were ones and zeros that you're comparing the actual chip response with, then actually it's a very easy problem to solve. And this problem was solved in the 1970s and 1980s. In real life, what happens is that when you actually simulate a chip to figure out what its response should be, you cannot exactly always tell whether the chip is going to produce a 0 or a 1. What you do is that you say the chip is going to produce an unknown. That means that bit you cannot test because you do not know whether that bit should be a 0 or a 1. So when you have a real chip that's producing a 0 or a 1, you don't have any reference and you have to ignore that particular bit, basically. Everything that was known before the work that I did at Intel, as soon as you have a few unknowns, everything would be completely messed up. You could not do anything. It had been a problem in the field for 30 years. I actually had a bright idea within a month of joining Intel of how to get around that problem. So when I had this idea, there were other groups inside Intel that were trying to solve the same problem, because this was a very well-known problem in the field. So the first reaction that the senior people had was, who is this recent college grad? He claims that he can solve a problem that we have been trying to solve for decades. I actually faced massive resistance inside the company. I was at Intel for around 4 years. The happy news was that by the time I left Intel, there were 40 products that were using that stuff. Today, I think almost all electronic systems actually use that stuff that I did at Intel. Also at that time at Intel, early 2000s, 90 nanometer technology was coming up. There were many reliability failure mechanisms that were not very visible in the previous generations that started becoming very important, such as radiation-induced soft errors. Neutrons from cosmic rays would come and hit your chip, and there would be secondary reactions that would actually cause bit flips inside the chip. These were big problems in space, but nobody would ever imagine that these would be problems for terrestrial. This is a major issue, especially for the cloud. It was a very exciting time in some sense to see these big challenges. I designed flip-flops that would self-correct themselves with respect to these things called soft errors. These are the kinds of things that I did at Intel. I continued that route, robustness of computing systems. I wanted to go back to academia because I liked academia. I said to myself that I should do something at Stanford that I wouldn't be doing at Intel. I was very fortunate that I ran into a colleague at Stanford, Philip Wong. He had a very distinguished career at IBM. We decided that we would work on nanosystems. How do you create actual working systems that provide a lot of benefits using nanotechnologies? How you transform materials and devices into actual working systems with large benefits. That started off the second area of my research, which is the nanosystems research. A few years back, I also decided to look into what I call problems of day after tomorrow. If you think of all this robustness stuff, design bugs, manufacturing defects, reliability, these are problems of today. We actually have to solve those problems. Otherwise, we would never have systems that the whole world relies on. Then if you think of those nanotechnologies and nanosystems, those are problems of tomorrow. When we started, nobody ever thought that anything beyond silicon would ever be practical. There was this announcement in 2022, TSMC and Infineon use resistive RAM for automotive processors instead of embedded flash. That's an example of a beyond silicon technology to actually build working systems, kind of pushing the boundaries of tomorrow. But then what I got really excited about is looking into problems of day after tomorrow. And I think one of the biggest challenges that we humankind have moving forward is to try to understand what's going on with the brain. So that sort of is an area that I decided to work on from both angles. One is, since I'm a digital systems person, people talk about embedded systems. Nothing can be more embedded and more constrained than something embedded inside the brain. You talk about power, you talk about energy, you talk about bandwidth, reliability, and robustness too. By embedding electronics inside the brain also allows us to get very close to neurons and to really try to understand what's going on inside the brain. These are kind of the areas that I work on.
That's totally fascinating. And a lot of these areas are close to my heart. As a product engineer on the Pentium chipset, when I was at Intel, my first industry job, we started seeing transient failures as well as on the tester. The tester technology has to be at least one generation ahead, which is very hard when you're designing state-of-the-art chips. So we started seeing failure modes and the amount of data was exploding. So I contributed to reducing data on the test heads, real time full speed testing. I was very fortunate to get an Intel Recognition Award. That was such an honor. A lot of the technology had to find its way into design automation. That's how I joined startups which are acquired by Cadence and Synopsys. This is amazing also that I spent quite a bit of time on neuroscience at Stanford, more on the medical side, the neuroscience of compassion and happiness. And I have the same thought. So, have you done any work more recently on neuromorphic computing, or are you talking about something else when you're talking about the brain computer interface?
First of all, two things that are going on. One thing is people are using conventional electronics. They are trying to see that if they can build computing systems that do useful things. Some of this can be brain inspired. Originally, the neural nets, when they first started, people used to talk about perceptrons. I guess every generation thinks that they have understood how the human brain works. Today, if you look at neural nets, I really do not think that anybody would say that they have anything to do with the actual brain, but they're actually very useful. There are these brain inspired computing models. Spiking neural nets are an example of that. There is this notion of what is called hyperdimensional computing. Oftentimes, those approaches are called neuromorphic. I have worked on hyperdimensional. I generally do not work too much on the neuromorphic side of things. I distinguish between classical neural nets versus neuromorphic. That's using conventional electronics. How do you implement systems that do meaningful things? What I'm trying to do with my brain machine interface work, basically, this is my work with Professor E.J. Chichilniski at Stanford. And our project is called the Artificial Retina Project. If you insert an electronic chip inside the retina, and it has electrodes that are connecting to neurons electrically. Let's say that there are certain causes of blindness where the front part of the eye is gone, but the neurons and the optic nerve are still working fine. Then, in theory, you should be able to wirelessly transmit an image into that chip, and that chip should be able to figure out that which specific neurons have to be stimulated to what degree, in what ways. And if we are able to do that, then we should be able to pass the native code through the optic nerve. So a blind person should be able to see, or even normal human beings should be able to have multiple visions. That is the big picture idea. This is the Stanford Artificial Retina Project. That's like programming. You have a physical substrate. In our case, these are transistors, essentially. And you have a higher level task, maybe sorting numbers. And what do? We write a program at that high level language, and there is a compiler that then translates that thing into today's voltage pulses, because that's how today's CMOS technology works. So then these voltage pulses are applied in some specific orders so that your underlying physical substrate actually does something and produces some result. What you get is sorted numbers. If you take that analogy, it's a very similar thing. You have the neurons, and you actually have a chip with some electrodes, and you figure out which electrodes, how much current has to be stimulated so that the right kind of pulses, the right kind of encoding gets into the optic nerve so that you can recreate the native code. So from that standpoint, it's like programming the real brain. That's what I'm working on for the brain machine interface project.
This is indeed fascinating. There's been a lot of news about Neuralink now getting slowly into real world. What you're doing, the brain computer interface work related to that, number one. And number two, how do you make sure that it's used for ethical purposes?
If you think of what Neuralink is trying to do, I need to bring up somebody who is very dear to my heart. Professor Krishna Shenoy used to be my colleague at Stanford. Absolutely brilliant person and a very generous person. Unfortunately, he passed away in February last year. In my mind, what Neuralink is doing is have devices like people are thinking and their thoughts are translated into actions. Krishna did pioneering work in that field, like patients being able to grab water and things like that. That was Krishna's work. This is called true impact. Krishna is not with us anymore. His legacy is just, incredible. I used to tell Krishna that my mom was more excited about his work, what Neuralink is trying to do, like grabbing stuff from the brain and actuating the external world. That's sort of my understanding of what Neuralink is doing. What we are trying to do is kind of closed loop. Of course, we collect data. There is a calibration mode where you poke neurons through the electrodes and try to characterize the physical substrate. When you transmit that image, it's actually going into the brain, into your retina in our case. We are actually stimulating the neurons themselves. So from that standpoint, it's different from this other world. I think one needs to be very careful about the ethics of all this. The definition of what is ethical, that also changes. Whatever was ethical 50 years back is not ethical anymore, and vice versa. Even in medical science, certain kinds of surgery was not ethical in the old days, and today, which is routine. How do you maintain security so that somebody cannot hack into your thing and do unethical things? I think from a technology development standpoint, one needs to make progress in each of these things. The potential, the promise of these technologies, the impact they can have on human beings or the world is just incredible. Ethics cannot be an afterthought, but at the same time, it's very important that ethical concerns should not stop technology development. It should happen in a symbiotic way.
What you're saying completely rings true for me. Ethics changes, but the technology itself can be used in very productive and meaningful ways. You worked on nanosystems, nanotech. How did you get into that?
The early days of computing were dominated by what? Electromechanical relays, vacuum tubes, discrete transistors. In 1958, modern integrated circuits were born. The Nobel lecture by Kilby was an eye-opener for me. What was going on in 1958 is not very different from what's going on right now. In his Nobel lectures, Kilby talks about this. The naysayers of integrated circuits had three concerns. The first concern was that the yield will never be high enough to be profitable. The second concern was the materials people were using to build transistors at that time were very different from what would be used for integrated circuits. And the third one, it says that the true transistor people did not want to see their elegant devices being messed up by all the other stuff on the chip, which we call parasitic. He didn't have a retort. All these concerns were essentially true. But as we all know, we rely on integrated circuits to do everything today. Now, if you fast forward, what's going on today? Everybody talks about AI ML as one of the driving applications. I call it abundant data computing. Essentially, you process enormous amounts of data for useful purposes. If you look at what's going on there are several walls that we are facing today. The first wall is what is called the memory wall. Enormous amount of time and energy are spent trying to go back and forth between the computing chip and the memory chip, shuttling data back and forth. That's how you spend most of your time for these applications that we care about. This memory wall is not a new idea. The way we actually address the memory wall is by miniaturization. You just go and make things smaller in a given area. You can pack more and more transistors. The humongous chunk of those more and more transistors that you pack, you just dedicate that for memory. The fact that you can keep making things smaller and smaller and smaller, that itself is running out of steam. This is what I call the miniaturization wall. Static random access memory, SRAM cells are not getting smaller anymore. So the miniaturization wall has hit SRAM. The question really is, how long can you just keep making things smaller? Why is this important, this miniaturization wall? Because remember that our way of dealing with the memory wall had been through miniaturization so that we can put more and more memory on a chip. But if you have this miniaturization wall, you cannot put more and more memory on a chip anymore. For getting a lot of performance, a lot of energy efficiency, the world relies on computers to be able to do all this AI, ML, and abundant data computing. This is where our work on nanosystems comes into play. We try to get out of this paradigm to overcome these challenges. In spite of major advances over the past 60 years, computing today is pretty basic. You actually have this computing chip, which is a two-dimensional plane of transistors with some wire stacks in the third dimension. And as I said, that the computing chip and the memory chip sit very far from each other. Shuttling data back and forth takes up a lot of time and energy. Instead, what we are pursuing is what is, we call it NEXT, which stands for N3XT, or Nano Engineered Computing Systems Technology. The idea is that we will actually create many layers of very efficient logic for computing purposes and very dense memory that are deeply interleaved with respect to each other. So essentially, we are building a high rise. So we are no longer stuck in a two-dimensional plane anymore. So that overcomes the miniaturization wall. And also that overcomes the memory wall simultaneously. Now, if you build a high rise, what is the single most thing that you have to make sure in a high rise? There are many densely populated floors. The high rise should have a lot of elevators between the floors. Similarly, if you think of future chips, if you are building these three-dimensional structures, these three-dimensional chips, you have to make sure that there are a lot of connections, very dense connections between the various layers so that you can move data around massively between the various layers to do your computation. Where does nanotechnology comes into play? You use nanotechnologies, which could be new kinds of transistors, new kinds of memory cells, new kinds of fabrication as well. What is absolutely important is that you enable new architectures that are not possible or very difficult with existing technologies. Otherwise, if you just take an existing architecture, let's say an NVIDIA chip or an Apple chip or an Intel chip, and you just say, well, I'm just going to go and replace my existing transistors with a new transistor, the benefits that you would be getting are very small. You would still be stuck by the fundamental bottlenecks of existing architectures, which is the memory wall and the miniaturization wall we talked about. Since it costs a lot of money to do the research and to create the technology for these new nano devices and nano fabrication, the benefits that you would get must be very high. Our target is 100 to 1000x improvement in what I call system level energy delay product. You can actually do a lot of work at a very low energy. You should be 100 to 1000 times better than what you can achieve today. That's where these three-dimensional chips become very relevant, because it's very difficult to build these very dense three-dimensional chips using silicon transistors. If you try to build a silicon transistor on the 5th floor of your chip, to build a silicon transistor takes a very high temperature of 1000 degrees C, which means everything else that you built underneath before you went to the 5th floor, those would be severely damaged. And this is what is called the thermal budget of fabrication, which is a very fundamental thing. So now with these new technologies, not only do they bring unique benefits with respect to fast speed and low energy or very dense storage, you can naturally build them at a very low temperature of less than 400 degrees C, which then enables monolithic three-dimensional integration. Think of today's chips, where on various layers of the chip, you have logic and memory that can do all sorts of things, and with very dense vertical connections, because the vertical connections that are used between wires in today's chips are probably the densest vertical connections known to humankind. Now, this all sounds academic, or this actually practical. All this is work that I have done in collaboration with my students and my collaborators. What we have achieved is actually this proverbial lab to fab. We demonstrated actual working systems out of these nanotechnologies at Stanford using the Stanford fab. In 2013, my former PhD student, McCluskey, working with all of us, demonstrated the first carbon nanotube computer. That was actually the first processor anyone was ever able to build using one of these new nanotechnologies beyond silicon nanotechnologies that promise a lot of energy efficiency benefits. In 2017, we were able to demonstrate this kind of a three-dimensional chip. This was also Max Schulacker's, that was the last chapter of his PhD thesis. He went on to become a professor at MIT. In his group in 2019, he demonstrated the first RISC-V microprocessor fully built with carbon nanotube transistors. What is truly exciting is that in actual industrial fabs, we have been able to establish this technology. So Max Schulacke established carbon nanotubes at Analog Devices, ADI. As part of a major DARPA program, we have established carbon nanotube transistors, resistive RAM memories. They're this ultra-dense monolithic three-dimensional integration on top of silicon CMOS at the Skywater Technology Foundry, which is a US foundry. We have been able to build actual chips using these technologies that work in a silicon fab. That's kind of is a journey of NanoSystems. Ultimately, these are the ways of achieving that 100 to 1000x improvement in system level energy delay product.
Wow, you did cover a lot of ground, and I'm so grateful that you're doing that. As you said, the memory wall, the miniaturization wall, I can see the derivative walls that have been created, such as the energy wall, the energy footprint.
Absolutely. It's funny. You would say on my slides, I show all that the power wall, the cooling wall, the resilience wall.
Yes.
We should talk about the resilience wall a little bit. All these walls are coming fundamentally from this memory wall and the miniaturization wall. Cooling wall, how do you cool your chips?
In fact, as a product engineer early in my career, we faced this in the zero 0.9 micron, that was like thousands of times slower chips, much earlier. 1 micron, 0.9 micron, which was the technology used around the Pentium chips. I'm glad you're bringing up a lot of these things. I want to go back to school again to learn about the challenges that people are facing. Could you go a little bit deeper into what are carbon nanotubes and how it's going to change the energy footprint? And also into resistive RAMs, what will they do for people?
Carbon nanotubes are nanocylinders of graphene. We all have written with a pencil. The tip of the pencil is made of graphite. Instead of the tip of a pencil, if you had a layer of graphite, now if you put a scotch tape and you were able to just peel off the layers and layers and layers of graphite, then ultimately you might be left with only one layer of something which is called graphene. There was a Nobel Prize for graphene. If you roll this graphene into a cylinder, you would get what is called a nanotube. The diameter of the cylinder we are talking about is like 1 nanometer. That's what is called a nanotube or a carbon nanotube. Now, how is this carbon nanotube useful for anything that we do in computing? If you think of a transistor, you have a source and a drain, and in the middle there is a channel. What is a source and a drain? You can think of it as water and going through a pipe. There's a tap and you're sending water from one side to the other side. That's pretty much what a transistor does. My colleague Philip Wong, he explains it this way. He says, what kind of a water pipe do you want? When the tap is on, you want a lot of water flow very quickly through that pipe so that you don't have to wait on the other side for water to come in. That would be equivalent of you want a lot of current to flow through the channel of your transistor. That's the first thing. The second thing is you want that pipe to be very thin so that you apply a little pressure and the pipe turns off. If you had a very thick, massive pipe, how much force you have to put in so that the water cannot flow through the pipe, which means that it should be turned off very easily. And when it is turned on, it would be passing a lot of current. Now, Mother Nature has created those nanotubes. They're so thin that they can conduct a lot of current. Because they're so thin, the amount of effort that it takes to turn them off are very small. The third piece is, remember Kilby in his Nobel lecture was talking about how these transistor people were upset with all these parasitics on the chip. If you fundamentally have a very small structure, then the parasitics that are associated with the small structure are also very small. Parasitics wise, also you should be doing very well. By the way, the first carbon nanotube transistors were demonstrated in 1998 independently by Delft University, Professor Decker there, and also by IBM Research. That was 1998. So then you wondered, if carbon nanotubes are so good, they can bring a lot of energy efficiency benefits in digital computing. At a very low energy, you can get your work done very quickly. If you replace your silicon transistors with carbon nanotube transistors, if that is all true, then how come we do not have carbon nanotube transistors inside our cell phones today? Even though the first carbon nanotube transistors were demonstrated in 1998, nobody could build any meaningful circuits for a very long time. You have these tiny little strings of nanotubes. Things are so small, it's very difficult to exactly control the electrical properties and how exactly they're aligned on a substrate. Think of a bowl of noodles. They're very unruly. Then how can you actually build working circuits out of such unruly things? That stopped the community to be able to build actual working digital systems. This is now NanoSystems come into play. I'm very thankful to my colleagues, to my collaborators and my students. They came up with this idea of what we call imperfection immune paradigm, which is how do you combine new kinds of fabrication techniques with new kinds of design techniques so that a combination of the two can get around these problems. For those of you that are familiar with fault tolerance and redundancy, we are not talking about that kind of stuff. We are not talking about, how you put a massive redundancy to get around these problems. The massive redundancy will kill the energy efficiency benefits of these new kinds of materials. So we were able to create those techniques. And in 2013, we were able to demonstrate a complete microprocessor built out of carbon. Since then, we have been able to build things starting at the university labs. Today, it's actually working in actual silicon fabs, which is something that we are very proud of. Today, given all these advances, now major players are actually investing in carbon nanotubes. Carbon nanotube transistors can be built at a low temperature. So they naturally enable these three-dimensional systems, the key to overcoming the memory wall and the miniaturization.
That's truly amazing. Resistive RAMs, in what ways are they contributing?
We talked about how SRAM is not scaling anymore. You need very dense memory. We know of flash, and we have embedded flash, DRAM, SRAM. All of those are facing a lot of challenges. For a very long time, people used to think that there would be this one memory technology, the universal memory. We understand today, probably there won't be any single universal memory technology nanotechnology. That's where it gives rise to a wide variety of memory technologies. And one of the technologies in that wide variety is resistive RAM or RRAM. There are other memory technologies called MRAM or magnetoresistive RAM. And resistive RAM has two electrodes and you have a dielectric in between. Instead of storing charge, if you could modulate the resistance of the dielectric between two metal electrodes, then if you have a high resistance versus a low resistance, you could say one stores a 0, the other stores a 1. Then it's a memory. If you were able to change the resistance in a very fine way, you could store 0, 1, 2, and 3. You could store 0 through 15. That would be equivalent to storing 4 bits inside. That's what resistive RAM is. Device technology people have been working on resistive RAM for a long time. They have made wonderful achievements. Around 2016, a major French organization called CEA-Leti approached me and they were like, if we gave you resistive RAM on top of some silicon CMOS, what would you like to build? At that time, nobody ever demonstrated anything end-to-end actual working system using this resistive RAM. We took on that project at ISSCC 2019. Tony Wu, my former PhD student, he actually an IoT non-volatile microcontroller. It's for the edge Internet of Things. This chip, it sleeps for a very long time. It wakes up, it does its job and sleeps again. Since you are storing data in resistance, when you turn the power off, it continues to keep the data, which is a non-volatile memory. At that time, people were using embedded flash for those kinds of non-volatile microcontrollers. In that paper, we were able to show that you could have an order of magnitude improvement in battery life if you were using this resistive RAM versus embedded flash. There are many reasons for that. You have to re-architect the system. It's not just replacing one thing with another. These were one of the first end-to-end systems that anybody was ever able to build using resistive RAM and show massive benefits. There was a lot of skepticism from the industry. We are comparing with an industry chip, apples to apples, and showing this 10x improvement in battery life. When an academic group does that, questions are always raised. Is that a correct comparison? Long story short, November 2022, there was a massive announcement jointly by TSMC and Infineon that their microcontrollers, those are non-volatile microcontrollers for cars, they're going to replace their embedded flash with this resistive RAM. We didn't stop there. In collaboration with TSMC, we actually built the first AI hardware using foundry resistive RAM that can do both inference and training at the edge. So now, even before you think of this 3D and stuff that I was talking about, that itself has its roadmap, two really important things. First of all, even though we had access to resistive RAM, the principles that we created, the architectural and design principles, work for other kinds of memories too, such as magnetic RAM. That's number one. And number two, this resistive RAM technologies, again, can be built at a very low temperature of less than 400 degrees C on the upper layers. Remember, to get around this memory wall and the miniaturization wall, you need many layers of efficient logic and dense memory. So this combination of these carbon nanotubes and resistive RAM in this monolithic 3D stack becomes extremely important, and that's something that we established at Skywater. Now we actually have working hardware prototypes coming from an industry silicon foundry.
Professor Subhasish Mitra, you've covered so much in one short video. This could have as well been 3 graduate lectures on X compaction, resistive RAMs, carbon nanotubes, and I can see the synergy between all of these things to make it possible to go beyond where we are stuck today, not just memory walls and miniaturization wall. A big concern that the amount of energy taken, for example, by a generative AI. Today, it may not be feasible to scale it to billions of people. With these technologies, we will be able to do what the human brain is doing, which is a lot of that computation at a much lower energy point, therefore reducing thermal footprint as well.
I do want to say one thing. This is important for people that watch this video. This was in the middle of COVID. I get a phone call from Google. Our existing test methods are not catching defective chips. Today, in the cloud, at the rate of roughly 1 in 1,000 chips are defective. They're actually producing erroneous results without people knowing that the results are erroneous. This is called silent data corruption. We cannot actually find defective chips with our existing methods. This is a massive issue in technology. If we cannot provide defect-free chips, the world can't rely on any of these things that we are doing, moving forward, there are incredible opportunities, almost like once in a lifetime opportunities to redefine everything, design verification, test, technology, and applications. Really exciting times.
Indeed, indeed. And in fact, to people out there who are listening, some of you who may not be from the realm of hardware technology, this is cutting edge. There are real humans working on this, not robots, to find ways to make it possible to have safe, reliable technologies. Silent data corruption is a real issue. It needs to be solved so that we can scale. Energy
Otherwise,
is
the
a
world
real
cannot
issue.
trust any of these things. Our trust in the foundations of computing will be shaken.
I remember we hit into that kind of a wall way back in the early 90s with the famous Pentium bug, which led to formal verification techniques. Now we are hitting another wall when chips are at least a million times faster.
And bigger than what it was before.
As you correctly pointed out, all these challenges are now presenting a huge once in a lifetime opportunity of redefining it from maybe siliconomy to going towards carbonomy, having carbon as the basis, possibly, or graphene as the basis. And only time will tell which of these technologies will become the dominant technologies, maybe even reduce the number of rare metals and rare elements that we have to use to create these technologies. So, again, I'm very grateful and thank you very much. And to people out there, this is why I talk to people from various disciplines. If you are seeing challenges and solutions in your area, in different walks of life, please come forward. I'd love to hear from you. I would love to see how it can make it a sustainable, energy efficient, reliable world going forward. Thanks again, Dr. Mitra.
Thank you very much for having me. Appreciate it.